All right. Well, thank you everyone for coming to this talk. It's a privilege to be presenting to you all today. So the topic that I chose is graph analytics, TinkerPop Vertex Programs, or GraphFrames. Now, if you don't know what either of those are, hopefully by the end of this hour you will. Now, to set the tone, we are going to talk a little bit about theory. We are going to work up to applications, and then I'm actually going to run some demos for you. And these demos, one is going to be what you call like maybe a toy graph with a few thousands of vertices, and then we're actually going to build on that and actually run a demo, and I'm going to show you how to run some algorithms of your own on graphs that are in the tens of millions of vertices and the billions of edges. So hopefully by the end of this, you can take some code away, some learning away, and actually do that on your own. Now, one more thing is just that this is a little more, it's a little more focused towards developers. I want to share with you my journey towards figuring out how to really learn how to write algorithms for graphs and scale those. So with that, let's get started. So my data is in a large graph. Now what? I want to try and extract some insights from it. I potentially want to write some custom algorithms. Mutate it, again, extract insights. Now, where do you get started? When you Google around, you look at GitHub, you look at various talks, you will get bombarded with so many different types of frameworks you can use, the types of tools you can use. Up here, I have 3 common ones. There's a bunch of other ones that you can look at. Piccolo is another one. Now, Giraffe, GraphLab, GraphX, GraphFrames are 3 of the big ones that you'll see when you actually go and do a Google search, or you go look around for papers. But what do you choose? So I put my developer hat on, and I kind of have 2 rubrics. One is how easy is it to use? 2 is how performant is it? All right, so I started with performance. And what I found was kind of surprising. So there's a great talk at Spark Summit from Ankur Dev, where he talks about GraphX. I think it's later in the day, so you guys have probably heard what GraphX is. GraphX is it's essentially a graph API that sits on top of on Spark. Now, in this talk, he claimed that as you can see, that GraphX is faster. So I was like, all right, I mean, I like Spark. I know how to use Spark. Get started with that. But then I thought, hey, let's check out some of these other frameworks, like Giraffe. Here's Facebook claiming that Giraffe is a lot faster. So on one hand, I have somebody at Spark Summit saying, hey, GraphX is faster. Over here, somebody else is saying Giraffe is faster. Now I'm confused. By the way, GraphLab was also up there, but the reason why I kind of took that out of my pool of frameworks that I wanted to play around with was just that there wasn't as much documentation, and a lot of what I was finding was several years back. For those of you who don't know, GraphLab, I think they changed their name a few times, but they were acquired, I believe, by one of these big companies like Apple or something. So now at this point, I'm a little lost, because I guess there's a bunch of information out there, and I don't know what's accurate. So I try and pull things back one level. I try and see what is something common between all these frameworks. Now, if you haven't heard of this term before, and it seems a little complicated, I promise you by the end of this, it won't be. So back some time ago, there was a guy named Leslie Valiant. Okay, he came up with this this framework for both hardware architecture and software architecture for writing parallel programs. And it's called Bulk Synchronous Parallel, BSP. You read any paper on Vertex programs or graph algorithms, I don't want to say any, but a lot of them, they will talk they will at least touch upon BSP, or bulk synchronous parallel. What does that mean? Okay, I have various super steps, and in between I have barrier steps. What does that mean? I take some sort of function, UDF, I apply it to a partition, okay? What's going to happen is that I'm going to apply that function and then send out messages. Okay, I'm going to wait till all those messages have been sent. Then at my barrier step, I'm actually going to then, for the next step, I'm going to process them. But the barrier step, why that's there, is because I have to wait till all these messages have been sent. So that's where the term synchronous comes in, parallel. As you can see, this is all happening in parallel. Pretty straightforward, right? And in a second, we're going to build on this intuition and see how we can leverage this to, we can apply this towards graphs. Okay? Now, oh, one second. Upon reading a little bit more, I dug into how say, SparkX is built upon BSP, how Giraffe is built upon BSP. So I started doing some research into Giraffe. Now, Giraffe leverages MapReduce. If you look into it, there's a lot of talks, there's a lot of papers. And even some of the folks that worked on the project will tell you that they kind of hacked MapReduce to function as to work with BSP. I started to do a little more research, and I found out that it was a little more inefficient in the way that state is passed after every MapReduce step. Additionally, they saw some issues with supernodes. Also, it's a little complicated to get Giraffe up and running. Like, I had some issues. The code base hasn't really had, it's been a while since some folks have really touched it, so this got disqualified. For anyone who's interested in seeing the differences between BSP and MapReduce, there's a great paper right here. I will put this presentation up on my GitHub repo afterwards. Okay, so next, what I came upon was Preagle. What is Preagle? Of course, Google, you know, they've got a big graph problem. I'm sure you've heard of a bunch of people talking about PageRank today. Well, in comes Preagle. Google created Preagle. They based this off of BSP. All right? Now, what they found is that they can take BSP and apply it towards graphs. Now, how do you do that? Okay, well, you take a UDF, some sort of function, you apply it to a vertex. All right? So in the event of, let's say, PageRank, I get incoming messages from my vertices, do my calculation, send out messages. Do that iteratively, and then I converge upon my PageRank score. Now, that's pretty straightforward for me to understand. And with BSP, I don't have to worry about futures or other complexities that come with async programming. But yet, I can have some of the benefits of having my code run in parallel. Cool. So at this point, I've built up an intuition, and I know my next step. I am going to try out GraphFrames and TinkerPop. Now, notice how I haven't still covered what TinkerPop is. I will in a second. Why did I choose that? You know what? It's easy. It's just easy to use Spark. It's easy to set up. I can go on Amazon, provision a cluster, get started. There's a lot of backends that I can hook up into that are actually persisting my graph. Yeah, it's easy, super simple. So now TinkerPop. If you guys haven't attended a TinkerPop talk today yet, well, this is the stack. It's essentially the ability to traverse to have OLTP-based traversals, OLAP-based traversals, and build on up all the way up to a query language called Gremlin, and then you also have a server that can handle the request for you. So now what we're focusing on with Vertex programs is the graph computer for OLAP. All right? Now, what's a Vertex program? There's a great paper for those that want to get in deeper. It's a little bit out of scope for this talk, but it's called Thinking Like a Vertex. This actually brings in some of that asynchronous component that I was saying may complicate things if you're not familiar with that style of programming. Now, again, like with Preagle, you pass a UDF. Now, what I like about TinkerPop is it makes it super simple. I say what I want to do to my vertex. I specify a terminating condition. And then what I really like is that you can actually say, here's my local message to pass along the edge to along the edges to my neighbors, or I even have the ability to broadcast a global message. Now, this was pretty cool. If you look at the code, I have links to the code. Super simple to read. Here's how it looks. When you execute, you send a vertex program to the graph computer. And what it does is, obviously, you can't pass, well, not necessarily obviously, but it just doesn't make sense to pass code to every single vertex in your graph. I mean, that's a lot of objects for a really large graph. So what you're going to do is you're going to parallelize it. And you're going to send this vertex program to, you're going to essentially send it to like a cluster of vertices, or a partition of vertices, rather, excuse me. OK? So that's vertex programs. Now here is GraphFrames. It's an API on top of Spark. Now with GraphFrames, so I'm going to go a little quick through this because this can get pretty deep. But GraphFrames, what you need to know is that with Spark, we have data frames, data sets. Now that has what's called the Catalyst Optimizer, which are a bunch of rules which kind of abstract away a lot of the complexities of doing distributed computing. So it leverages that optimizer, all that code that's been built, and it gives you the GraphFrames API. Now, if you actually start looking back at the code, you'll see that a lot of GraphFrames, especially the algorithms, they make direct calls to the actual GraphX algorithms. But the benefit is, for those of you that are trying to get started and want to use, say, Python, well, GraphFrames API allows you to do that. So that's pretty cool. Again, you can dig into this a lot deeper. There's a lot of great talks on Spark Summit. I advise you just Google that. So now let's start talking about application and demo. So I'm going to demo to you PageRank with Vertex Programs, GraphFrames, and GraphX. All right, now what is PageRank? It's a centrality measure. So rather than just counting all the adjacent edges to see how the connectedness that I have, what I'm going to do is I'm going to use PageRank. Now, what PageRank is it's not just looking at, say, how many vertices that I have on this particular node. It's also looking at my neighboring vertices and seeing how connected they are. So as you can see, to get that information, I do have to do some iteration. So this isn't as simple as just, say, doing maybe like a simple count of all the edges for each vertex that I have. So here is a little GIF that will actually show you. So as you can see, going. And we're converging upon a certain error threshold that we've set here. That's our terminating condition. Go. So you guys can see what we're doing here. Now, next, for those of you that are interested, here is the implementation. I advise checking it out. It's actually, it's super elegant for a TinkerPop. I was actually amazed. I was blown away. Just a couple hundred lines of code. Here it is in GraphFrames. Here it is in GraphX. Like I said before, GraphFrames, like literally it makes a call directly to this. So maybe you want to check that out. All right. So let's get started. Now I need to bring up my screen over here. All right. So we're going to start with a toy graph. All right. So for those of you who don't know, Kevin Lawrence, if you want to learn about gremlin querying, want to learn about gremlin, highly advise you check out his book. He's got this really cool data set over here, which is kind of like a airplane data set if you want to check out the schema. Here it is. We're going to read in the data set, All right, now this is the cool part. That is literally all you need to call the PageRank code that was already built. That's it. Just run that. How cool is that? And over here, I actually have printed out the values. So it looks like Charles de Gaulle had the highest PageRank score. That's reflected as well with the GraphFrames algorithm. I'll show you that in a second. There were some differences, and that was a little alarming to me. GraphFrames actually yielded that Istanbul had the highest PageRank. That just didn't seem right, and I actually am like I'm a little skeptical about that, and that's very concerning. Not very, but I'm concerned. By the way, they both had the same error threshold. Everything was the same in terms of the parameters to run the algorithm. Next, now this is super cool. Now let's say I want to actually store the PageRank values in my graph to extract, say, real time in OLTP mode. Check this out. I just add this property, run these 4 lines of code, use a bulk update vertex program, and I can actually persist this into my graph with just these many lines. I thought that was super cool. So here I'm showing you that you can actually persist the PageRank. I promise you it wasn't there before. I actually put that in there with the code above. All right, here now this is a graph. It's a bit of a mess, but it's just to show you that, I can see how Charles de Gaulle has a high PageRank. That is all its immediate or adjacent vertices. Yeah, it's pretty dense. Makes sense. I believe it. Okay, now next, let's look at how we implement PageRank with Spark. All right, same graph. Now this is also pretty cool. Okay, now for the scope of this, I persisted the data in DSE graph. I'm going to talk why I did that in a bit. Again, I just found it super simple, but I converted it to open source GraphFrames so that we could see how that works. So over here, I specify over here. That's just that's a timer method I took from Stack Overflow to just time this. Graph name, specify the graph name. Here I get a DSE graph frame back, converted to an open source graph frame. Boom, run graph frame. Pretty cool, right? Get my results back. This is how I get my results back over here. It should be ordered by descending. I don't know why I did ascending. Over here it is in GraphX. Same thing, except 2 GraphX. Now I don't know how comfortable everyone was in Spark, but essentially the execution profile for these was almost identical, which makes sense because GraphFrames is calling GraphX, and they ran it almost the same amount of time. So we can look at the results over here, and this is kind of cool. TinkerPop Vertex Program, 58 seconds. GraphX GraphFrames, 438 seconds. Now, I wanted to see if this would scale to a much bigger graph. So I don't know if you guys have seen the data set, the Twitter 2010 data set. 41.6 million vertices, 1.46 billion edges. Now, I underestimated how long this was going to take. So if you guys want the results, my job is still running. Hopefully by the end of the week, I'll have the results. But I have the code, and if you guys want to run it, go ahead. But yeah, unfortunately, I don't have the results for today. I apologize. It would have been cool, but now, let's go over here.
How long has it been running?
I don't want to tell you. I literally thought it would take a few hours. It's been running for days. But I could have messed something up on my end, so we'll see. Should have had better error handling, I guess. Now, this is the cool part. This is the cool part. So now I took that data set, and with less than 50 lines of code, I loaded Twitter 2010 into DSE Graph, loaded it. Now, this is cool. So if anyone who hasn't used Spark before, the total time it took, I guess you could say sequential time, was over 300 hours of processing time. I did that in just a few hours in parallel. That's pretty cool. In just a few lines of code, I can show you. For anyone who's interested, just go over to GitHub, and you can check it out. Just right here. Oops. Here you go. That's it. That's all it took to load that massive graph. So if you're interested, over here, you can build this. It's ready to build. I ran it against DSE 6.0.2. Again, I'm not the best documenter. I openly admit it. So I have my email here at the end. If you have any issues and you want to run this, just shoot me an email. Happy to help out. I also have the code for you to actually submit the jar for, or to actually submit a Spark job for running PageRank. So you can also go on my GitHub page and check that out. Oh yeah, so over here, I had it up. I didn't know whether it made sense to go through code for this. It seems like it's probably not a good idea. But here you can see, like, it's just, here's the TinkerPop Vertex program. I found it incredible. In just a few hundred lines of code, you can literally implement PageRank, custom PageRank. So with that, I'll close things off. Now, really, my goal for this talk was to build some intuition and go talk about some potential applications. Now, and also run through some code. So to summarize, what I found out is that I think I personally like using Vertex programs and would like to in the future even more for writing some custom code for, say, potentially for writing some lightweight jobs that I constantly want running in an environment. Not everyone can have a Spark cluster where they can just be running jobs for days on end. It's expensive. It's expensive. This adds up. Six M4 machines running for several days, not on spot pricing, that adds up. And I'm sure you're going to want to run this over and over and over. So one potential use case that I thought of, I was working with a customer, and they're doing entity resolution. And what they're doing is that they're pointing, they have, like, say, a master identity over here with some properties on this graph. They're connecting some other vertices, saying resolve to, but each of the resolve to vertices has different properties on it that they want to be able to search on up here. So getting this, the properties up here and bringing them up, having a lightweight Vertex program that's just using local messages, no global messages, I think that that's a pretty cool use case. I know I don't have the data up here, but I'm almost positive that GraphFrames is going to win on the big graph. How do I know that? Somebody told me. But it will be confirmed. OK, so if you want to get in touch with me, GitHub, pmehra7, email me, parsmehra@datastax.com. You know, Lynn put up something about Twitter. I don't use Twitter. So that's it. If you guys have any questions, fire away. Feel free to check out the GitHub repo and start running some graph algorithms of your own. Thank you.
So the TinkerPop Vertex program, it doesn't use Spark at all?
No, so if you go back up here, they used to run, they had a Giraffe computer and a Spark computer. You do need an execution engine, right? So what they're actually doing is that they are leveraging Spark in the back end, yes.
But is it a very, like, the fact that it's been running for several days, but you haven't, I assume you're not running into GC issues, you're not running any kind of big.
No.
I mean, the way that algorithm works, is it a pretty lightweight, pretty manageable thing to operate?
So we could look, so yes and no. The communication costs are high. No, I'm not seeing a lot of GC issues. GC is pretty low. So for those of you that haven't used Spark before, there's a Spark UI, which has a lot of beautiful metrics. Here is another Spark job that I'm running, so I could potentially just show you. Oh, well, no, I can't. Did my VPN get disconnected? Oh, no, it's done. That's why I can't show you. But you can actually see some really cool stats like garbage collection, shuffling, and potentially all the network costs that come with it. The execution profiles are very different, but I haven't yet run into any issues. I have heard from a few of the folks that are actually core committers on the project that they think that the TinkerPop Vertex program will probably time out on really large graphs. But no, I have not run into, for example, GC issues or anything that I would deem as being unmanageable just yet.